In addition to the range, another measure of dispersion is called the standard deviation. Whereas the range was a very simple calculation, the standard deviation is much more involved. Now, the standard deviation is the average distance between each data point and the mean. So the standard deviation is a measure of dispersion. And recall that the mean is a measure of central tendency. So when we calculate the standard deviation, we're looking at the average distance between each data point and the mean. We can visualize the meaning of the standard deviation if we compare two data sets. Let's suppose that I have two data sets and I'm going to arrange each of these data sets from smallest to largest on a number line. Now, because the mean is a measure of central tendency, the mean for each data set is going to tend towards the center. Now, one data set may be closely packed near its measure of central tendency, the mean, whereas another data set may be more dispersed or spread out on that number line. If I find the distance between each point and the mean, and then I average those distances, that's going to give me the standard deviation. So if I look at the first data set and compare it to the second one, the first one has a smaller standard deviation. And the second data set has a larger standard deviation. That is, the average distance between each point and the mean is larger in this second data set than it is on the data set on the right. And again, we're looking at the average distance between each point and the mean. So smaller and larger standard deviation, those words are relative to these two examples, just so you can begin to visualize. The standard deviation is measuring the spread of this data. Now let's consider, how do we calculate something like this? We are calculating an average, and when we find an average, we add up all the numbers and we divide by how many we have. So when we calculate the average distance between each data point and the mean, the first thing we need to do is find all of those distances. So let's suppose, using our second data set here, that we name each data point x sub 1, x sub 2, x sub 3. We're going to have any number of data points. I'm just going to say ... We're going to continue naming our data points like so up to x sub n. So we're going to say n is the number of data points. And recall, x bar is the mean. So to find the distance between one data point and the mean, I'm going to calculate the difference. I'm going to take the difference between x1 and x bar. So notice that's what I have right here. So this first difference is the distance between the first data point and the mean. Okay, notice, ignore the square for a minute. Notice here I have x2 minus x bar. That's calculating the distance between x2 and the mean. So that represents the distance between x sub 2 and the mean. So I'm going to continue finding these differences. Oops, typo, that should say x sub n. We end with the last one. So the difference between each data point and the mean gives me the distance between each data point and the mean. Now, there's a little bit of a problem if I add those distances together. So at the moment, I'm ignoring the squares. If I add those distances together, because everything is dispersed about the mean, the sum of those distances is going to give me 0. Because remember, some of the data points are below the mean, so when I find that difference, I'm going to get a negative number. Some of our data points are above the mean, so when I find that difference, I'm going to get a positive number. If I add up all of those distances, they're all going to sum to 0. So in order to have something that we can work with, we're going to go back and we're going to square all of those distances. Remember, when you square a negative number, you get a positive number. So that when I add all of those values together, I have something with substance. I've got a positive number. Now, we're going to cancel that out in a way with the last step by taking the square root of our result. Not quite inverse operations, but this is how we calculate our standard deviation. Now, when we add all of our distances, we're going to divide by not the number that we have, but the number minus 1. So it's related to calculating an average, but there's a few twists and turns here. So the shortcut formula for this, the standard deviation is equal to the square root of, remember this big capital sigma? We learned that that represents a summation. So I'm going to add all of the squares of the differences between each data point and the mean. I'm going to divide by n minus 1, and I'll take the square root of that. That's what we call the standard deviation. The standard deviation is measuring the spread of data, and you can think of it as the average distance between each data point and the mean. A data set with a smaller standard deviation means it's more condensed around the mean. And a data set with a larger standard deviation simply means it's more dispersed and spread out on either side of the mean. Now, the formula looks a little bit intimidating, but we're going to make use of tables to build our way up to evaluating that formula step by step. Let's try this on example 3. It says the data set gives the number of platinum albums for 5 male artists. So Garth Brooks, 145, Elvis Presley, 104, Billy Joel, 80, Michael Jackson, 71, and Elton John, 65. If we want to calculate the standard deviation, we're definitely going to need the mean. So let's begin by calculating the mean. So to calculate the mean represented by x bar, we add all of our data points. And we divide by how many data points we have. So it looks like we have 5 there. So make a note. N is 5 data points. So let's plug that into our calculator and determine the sum. 145 plus 104 plus 80 plus 71 plus 65. So our sum is 465. We're going to divide that by 5, and we'll have the average number of platinum albums per artist. Looks like 93 albums is our mean, x bar. That is a measure of central tendency, and that's the first step in calculating the standard deviation. Now, in order to calculate the standard deviation, we're going to need to find the difference between each data point and the mean. Then we're going to square all of those differences, and then we're going to sum those differences. So that's a whole lot of steps. When we're calculating a standard deviation, it's really helpful if we do it in the form of a table. So that's what we're going to do here on example B. It says use the table given to calculate the standard deviation. If you'll build a table like this for the problems on your homework, then you can calculate that standard deviation one step at a time. So notice under the column called X, we've got all of our data points. Next, we need to find the difference between each data point and the mean. And don't forget, the mean was 93. So I'm going to take each data point and subtract the mean. I'm just going to type that right into the calculator to get that difference. So we end up with 52 for that first spot. So again, each spot, we're going to subtract the mean. And I'm going to show you a guaranteed way to check your work on this part. Okay, so I'm set up. 104 minus 93 gives us 11. 80 minus 93, notice this one comes out to be negative 13. Leave it negative as is. 71 minus 93 gives us negative 22. And 65 minus 93, we get another negative number of negative 28. Now, watch what happens when I sum this column. We have 52 plus 11 plus negative 13 plus negative 22 plus negative 28. We end up with 0 every single time. Okay, so when you find the difference between each data point and the mean, it should always sum to 0. If it sums to something else, then you've made a mistake somewhere and you can go back and start checking your calculations. Next, we're going to square each of those differences. So recall from our formula, we've calculated all of these differences. Now we're going to go ahead and square those differences. We're building up to this formula little by little. So I'm going to take each of these values and square them, and I'm just going to do that with the calculator. Now, we have to be really careful with these negatives, the way we enter those into the calculator. We know that the square of a negative number always turns out to be a positive number. So the first two are pretty straightforward. To square, I'm just going to type my x squared button. 52 squared is 2704. 11 squared is 121. Now watch this. If I type in negative 13 squared without parentheses, the result is negative because the negative there is not being squared. So I have to be really careful to square this properly. If I put the negative in parentheses, the calculator will treat that as negative 13 times negative 13, which is positive 169. Now, another way is just to anticipate. I know the answer is going to come out to be positive, so I'm just going to square the positive form and make sure I record the positive number. Might save you a couple of buttons to press. Next one is 484, and then 28 squared is the same as negative 28 squared. We get 784. Okay, now that we've squared all of these differences, let's look where we are in our calculation up here. We have evaluated each one of these terms. I have the first difference squared, I have the second difference squared, all the way up to the last difference squared. So next what I want to do is add those together. And again, that is executing this big sigma over here. So I'm going to simply sum those numbers in the column. 2704 plus 121 plus 169 plus 484 plus 784. The sum there is 4,262. Now we're ready to calculate the standard deviation. So recall from our formula, the standard deviation is the square root of the sum of the difference between the data point and the mean squared divided by n minus 1. So let's plug in what we know. The sum of the difference between the data point and the mean squared is given by this number that we worked so hard to find with our table. So that's the number that we put in the numerator. Now, in the denominator, we don't just have n, we have n minus 1. Recall that we have 1, 2, 3, 4, 5 data points. So we're going to divide by not 5, but 4. So we need to find the square root of 4,262 divided by 4. I'm just going to type that directly into the calculator. To get the square root, we do our second key and the x squared button. Notice above the x squared button, you can see that radical there in blue. So I'm going to type in the radicand, 4,262 divided by 4, and we'll just round to the nearest tenth. We get 32.6 for our standard deviation. So 32.6 is the standard deviation. So if I glance back at this column where I found the difference between each data point and the mean, notice that 32.6, and of course ignoring all of the positives and negatives, look at the absolute values of those numbers. 32.6 is right in the middle of those numbers. The smallest there smallest absolute value is 11, the biggest is 52, and 32.6 is in the middle. So think of the standard deviation, again, as the average distance between each point and the mean. A larger standard deviation means your data set is more dispersed. A smaller standard deviation simply means that your data points are closer towards the middle, towards your mean. Now, to really understand how the standard deviation is helpful in analyzing a data set, we're going to work through this next example. Suppose that Karen and Gray go bowling. Their scores are listed below. So Karen has scores of 185, 190, 178, 184, 185, and 188. And Gray has scores 185, 200, 170, 210, 185, and 160. So let's see if we can answer the question, who is the better bowler? We're going to do this not just by making an opinion, but by actually using measures of central tendency and measures of dispersion to support our case. Who is the better bowler? So first of all, let's talk about measures of central tendency. Let's consider Karen's game to begin with. We're going to find her mean, median, and mode. Okay, notice we have 1, 2, 3, 4, 5, 6 games for each bowler. So let's go ahead and calculate Karen's mean. That is, I'm going to add up all her scores and divide by 6. I'm going to do it in one step on the calculator. So in parentheses, I'm going to add all of her scores together. Okay, that sum is contained in parentheses in the numerator, and then I'm going to divide by how many data points we have, and it looks like her mean score is 185. Now let's go ahead and find her median. The median is the data point that is right in the middle of the data set. Now don't forget, to find the median, we have to make sure that the numbers are in order from smallest to largest. So I'm just going to rearrange her scores from lowest to highest. She had 178. I'm going to mark them out as I go. She's got a couple of 185s right there in the middle, 188 and 190. Okay, so her scores are the same. I just have them rearranged. Now the median is the value that falls right in the middle. We're going to have to average the two middlemost values since we have an even number of data points. And if I average those two numbers, we're going to get a median of 185. So the median and the mean happen to be the same on this problem. Let's look at the mode. Remember, the mode is the most frequently occurring data point, and clearly that is 185. So her mean, median, and mode all turn out to be the same. That's kind of interesting. So let's look at Gray's scores. We're going to find his mean, median, and mode. So to find his mean, again, we're going to add up his scores. I'm going to do it all in one step with the calculator, which means I have to get this sum in the numerator in a set of parentheses. That way the calculator will evaluate the sum and then divide by 6. Okay, so there's the sum of his scores, close parentheses. We're going to divide by the number of data points that we have, which is 6, and his mean is also 185. Okay, let's find his median. Remember, the median is the number in the very middlemost position. So to correctly identify it, the data has to be in order from smallest to largest. So I'm going to rearrange his scores as well. Smallest to largest. And between the two middle positions, it looks like the median is 185, and I think you're starting to see the pattern. His mode, the most frequently occurring score for Gray, was 185. So at this point, I cannot distinguish between the two data sets using measures of central tendency alone. These data sets, even though they are obviously different, have different measures of central tendency. So let's go ahead and move on to measures of dispersion. Let's see if we can calculate the standard deviation for each bowler and use that to make our decision on who is the better bowler. Remembering that the standard deviation is quite an involved calculation, I'm going to make use of a table like we did for the example above. We're going to build it ourselves and work up to our standard deviation step by step. So the first thing I want to do is list all of Karen's scores. Then I'm going to find the difference between each score and the mean, and then we're going to square that difference, and we're going to sum that in a column. Okay, so I'm going to do this vertically, and I'm simply rewriting her scores, smallest to largest, 178, 184, two 185s in the middle, 188 and 190. Now, remembering that her mean was 185, I'm going to take each data point and subtract the mean. So if we take 178 and subtract 185, we're going to get -7. 184 minus 185 gives us -1. 185 minus 185 is 0. 188 minus 185 is 3, and 190 minus 185 is 5. Now remember, we can double check those values by adding them all up, and they should sum to 0. And again, in this case, they do exactly that. Okay, now we're going to square each of those values. Negative 7 times negative 7 is positive 49. Negative 1 squared is 1. Square those zeros to get 0. 3 squared is 9, and 5 squared is 25. So if we add those numbers together, let's see, we get 50, 75, 80. Looks like we're going to get a sum of 84. Okay, so just add those numbers up. Then Karen's standard deviation, I'm just going to write it to the side here, is going to be the square root of this sum, 84, divided by n minus 1. Remember, we subtract 1 from the number of data points. So we need to find the square root of 84 over 5. So I'm going to type that in, second square root, 84 divided by 5. And we will round to the nearest tenth, about 4.1. So Karen's standard deviation then is 4.1. Let's repeat this same process and we'll calculate Gray's standard deviation. So again, I'm going to list his data points, find the difference between each data point and the mean, and then square those differences. Then we'll use this table to work our way up to that complicated looking formula step by step. Remembering that his mean was also 185, we're going to subtract 185 from each of those numbers in the list. 160 minus 185 gives us negative 25. 170 minus 185 gives us negative 15. 185 minus 185 is 0. 200 minus 185 is 15, and 210 minus 185 is 25. Notice what happens. When I add those up, I end up with 0. Now we can square each of those values. 25 squared is 625. 15 squared is 225. If you're not familiar with squares, if you don't do it all day, every day like I do, then you can certainly use your calculator to evaluate those. Okay, let's sum these values. 625 plus 225 plus another 225 and a 625. So we end up with 1,700. Okay, that's the important number that goes in the numerator for our formula for standard deviation. Now again, remember, if you're wondering where this is coming from, I'm following this formula. This part we have accomplished by table. We have that number. Now we're going to divide by number of data points minus 1 and then take the square root of that. So remember, the number of data points that we have here is 6, so we're going to subtract 1 from that. We need to calculate the square root of 1,600 divided by 5. So from our calculator, the square root of 1,600 divided by 5, and if we round it to the nearest tenth, we get 17.9. So Gray's standard deviation is 17.9. So finally, we can see a difference between these two data sets. Both data sets have the same measures of central tendency, that's mean, median, and mode. However, they have different standard deviations. Karen's data set has a much smaller standard deviation, whereas Gray's is more dispersed with a larger standard deviation. So to answer the question, who's the better bowler, we should probably go with Karen. Karen, at least, is the most consistent bowler. Whereas Gray can sometimes hit those high scores, Karen bowls about the same every single time. So she is the most consistent bowler, so we might use that to conclude that she is the better bowler. Now, if Karen improves her skills and she retains that consistency, then she'll be a very strong bowler, right? If Gray could improve his consistency, maintaining those high scores, then he would also be an excellent bowler. But I'm going to go with Karen since I have the numbers to back it up. Since she has a smaller standard deviation, she's more consistent and she's the better bowler. All right, so the range and standard deviation are our typical measures of dispersion.